Good morning, everybody, and thank you very much for joining us. My name is Craig Milligan. I'm a road safety engineer and a co-founder of Microtraffic. Very pleased to be with you here today to talk about using surrogates, surrogate safety science to rapidly understand the safety impacts of Type 11 sign sheeting. Type 11 sign sheeting, if you're not familiar, is one of the ASTM standard levels of sign sheeting that has the highest levels of retroreflectivity. We're going to be talking about something called the Industry-Initiated Pooled Fund Research Project. We're going to be delivering some educational content on the science of retroreflectivity, surrogate safety, and human factors as it relates to the visual perception of signs and how that influences the driving task. And then we're going to introduce this study that we want to bring several DOTs together around this study to get a better scientific understanding of the safety, performance, and impacts of these signs. Just by way of outline, we're starting with the human factors topics. I'm going to cover that. Amanda, a road safety engineer also from Microtraffic, will be talking about how surrogates are starting to enable rapid assessments, powered by artificial intelligence, and how this is overcoming some limitations of crash data and delivering some impressive results. Todd Ballin from 3M, a senior product development specialist, will be talking about the science of retroreflectivity. And then we're going to come back to say this topic, rapid assessments in your DOT. What does it mean to join this pooled fund project? How you can actually participate in creating a new knowledge base that will guide practice within our profession for years to come. And myself, together with John Lower, Microtraffic's VP of Safety Partnerships, will be outlining that. Just a little more detail on who's presenting this. Microtraffic is a road safety company that developed a surrogate safety analytics technology. We're a global leader in this emerging field of road safety video analytics, and have helped 70 cities, diagnose road safety risks and take appropriate countermeasure actions in response to that, and measure risk reductions that they've achieved. And then 3M, of course, is a global provider of materials for various road safety applications, and a pioneer in the field of the science of retroreflectivity. Before we get into the first section on sign visibility, positive guidance, and human factors, I'm just going to pass it over to my colleague Amanda. She's going to pop up a couple poll questions. There's going to be a website for you to go to kind of interact with us during the webinar. So take it away, Amanda.
Thanks, Craig. If you don't mind navigating to www.menti.com, you'll be able to put in the code that's shown on the screen there. The code is 83416582. And we just want to do some initial icebreaker questions to get a better idea of who's in the audience today and what their understanding is of some of the topics we're going to be discussing. So please log in to go to menti.com either on your phone or on your laptop, and please keep that open during the presentation. We're going to come back to that and ask for some responses in between presentations just to keep the interaction a little bit higher during this webinar. So I see some poll responses coming in now. Oh. Sorry about that. There we go. Just give a minute as people continue to navigate to menti.com to give some responses there. Okay, so thanks for your feedback on that. The next question we were hoping to get some response back is just where you are right now. So we've reached out to a number of people in North America. I'll give you about 20 more seconds to fill out this first question, and then we'll advance to the next slide. Okay, the next question is, what city and country are you based in? So I put the example of Vancouver because we got Vancouver in Canada as well as in Washington. So we'd love to hear from you. You can type in your answer of what city and country you're coming from and calling in from today. Oh, cool. We got some international attendees. That's great.
Oh man, someone actually logged in from Vancouver, Washington.
Yeah, good.
Exactly your example. And we would have thought for sure that was Vancouver, Canada, if they hadn't put that.
Okay, great. The next question, we just want to get a bit of feedback from you guys about which statement best explains your understanding of surrogate safety measures. So as Craig mentioned, we're going to talk a bit about surrogate safety and near-miss analytics. So we'd love to hear what you've heard about this before, just to set the stage for the presentation today. Okay, glad to see there's some new audience members here when it comes to surrogate safety measures. Okay, and our final icebreaker question to kick us off today comes about ASTM type 11 sign sheeting. So which best explains your understanding of sign sheeting retroreflectivity and ASTM type 11? Great. Well, thank you so much for that feedback. It's exciting to see that there are a number of you who have heard of Type 11 and used it in the past, and we're excited to have you participate in our webinar today. Please keep that Menti tab open either on your phone or on your browser, as we're going to come back to it during this session and ask a few more questions, follow up after the speakers. So with that, I'm going to pass it back over to Craig to kick off our session today.
Hey, thanks a lot, Amanda. I love that too. I love seeing the answers pop in as we go along, and we've been using it for a few months now, and look forward to seeing your answers pop up for the future questions. I'm going to get right into this kind of little primer on human factors and how human factors ties into sign visibility. This is the area I'm passionate about, and I think that every traffic engineer should be pursuing in personal and professional development. I've dropped a couple of resources there that you can use to pursue further learning in human factors that provide a great foundation for learning and shaping your practice as a traffic engineer. The first thing I want to talk about is the driving task model. So I'm going to go through driving task model, positive guidance, and then human visual function, and then leading that into sign visibility. The first time that the driving task model was systematically analyzed, the people doing that broke it down, found over 1,000 specific things that on the road and during the driving task that drivers have to respond to. It's a very complex thing to do, to drive a vehicle. And so they started to break that down and categorize those different tasks that they have to do into a hierarchy. And as we talk about human factors and designing for humans on the roadway, it's useful to think about which area of the hierarchy are we trying to support with information, because when we give them information, we're trying to support them to achieve correct task execution. So the most common way to visualize the driving task model is in this three-level hierarchy of control, guidance, and navigation tasks. Each category of tasks requires information to handle correctly. So the control task is how, when we interact with the vehicle at its most basic level, the steering wheel, the accelerator, the brake, and our controlling functions like our lights and signal indications. And it's to stay on the path that we've selected or have previously determined in a different task that we want to do. So it's very much about execution. And we use sources, information sources like the instrument panel, the vibrations and the feelings that we get from the vehicle in order to execute control tasks. So for each task, and I'm not going to go into this in depth because of the time limitations on this webinar, but you could have an information prompt and then a control response. Information prompts are about hazards to the front, to the side, or things that you perceive, and then you've made a decision about what to do about it, and then that gets executed in a control task. And all the control tasks are about physically manipulating the vehicle. The second level, which is a bit more mental and less physical, is the guidance level of the driving task. And this gets confusing because I'm talking about the guidance task and later talking about positive guidance and the guidance we give to a road user, two separate things, okay? When we talk about the guidance level of task model, we're talking about the driver acting as the guide of their vehicle. And a guide decides the course, the path, the speed, where to go next, for hazard avoidance, for staying on alignment, and these kinds of things. So it refers to the ongoing selection of safe speed and path, but it's pretty kind of immediate selection. It's not talking about the whole trip level guidance. It means like now and the immediate next few parts of the trip. And control activities respond to guidance determination. So once the guide has kind of mentally made a decision, then it shifts over to control for execution. And what it requires is judgments, estimates, and predictions. And we base those judgments, estimates, and predictions on information that we take in. And it's based on both implicit and explicit rules. And so when we come to the information sources that are used for guidance, they can come from either the roadway itself, so we see a change in the alignment, and so then we're going to guide our vehicle through that curvature. They can come from traffic, so we can see our relative position to another vehicle and decide to guide our vehicle around that other vehicle. Or that kind of we have a relative velocity where we're closing in on a vehicle, and so we're going to select a different speed so that we don't strike that vehicle. So when we've made that selection, we've finished the guidance, and then when we execute that selection, that's over into the control task. So we get the information from roadway, from the traffic environment, and we also get the information from traffic control devices. So all kinds of signs, signals, pavement markings, and also any active feedback through ITS-based traffic control that sends information back to the driver based on live conditions. And the last component of the driving task model is navigation. And it refers to the activities involved in planning and executing a trip from start to finish. It is also very related to safety because the amount of mental space tied up in navigation for unfamiliar drivers or for areas where it's hard to kind of really know where the exit is, where the turn is, and stuff like that, decreases the amount of mental space we can allocate to guidance and control, so the immediate safe path and plan. And so you can have people, they miss an exit and then they get into stressful behavior, or just because they're so focused on the navigation. And this is a function of traffic too. Sometimes navigation is easy when traffic is light, but when it gets harder, when it gets busier, the navigation becomes harder, especially on freeways. So we have information sources for navigation that come pre-trip from our knowledge, our prior experience, maps, or verbal directions. And then we have two sources for navigation that come to us in transit, sources that are external to the vehicle. Again, we come to signs, and sources that are internal to the vehicle, so built-in navigation and GPS systems, and smartphone apps, and stuff like that. What I've meant to highlight here is that each level of the driving task model to successfully execute it requires information. And because of that, the concepts of positive guidance have been developed in the field of human factors and road safety. And that's what I want to briefly talk about next. Positive guidance, there's different senses of the word positive. And the sense of the word that we're talking about here is like, I'm positive, like I'm sure that what I'm doing is the right thing to do because the information has been provided in such a clear and unequivocal manner. So really, we're talking about providing users with the information they need to avoid hazards when and where they need it, and in a form where they can make the best use of the information, whether that's through signs, traffic control, or the visual perception of the alignment that we've provided in geometric design. Not all guidance information is positive guidance, right? Any information that would assist the user in selecting a speed or path is guidance information. But it's positive guidance when it's unequivocal, unambiguous, and conspicuous enough to meet decision site criteria. I also want to be clear here too, words are used in a few different senses. I'm not talking just about guide signs here, right? So while we're talking about information provided to the road user, that this can include regulatory signs, this can include the perception of the alignment that we intentionally provide, traffic signals. So I'm not talking about a section of the MUTCD on guide signs, any kind of information we provide to the road user. And when the guidance is positive, it's clear, unequivocal, and it's in time, it increases the chance of drivers making the right decision. And positive guidance has a lot to do with avoiding hazards. That's the goal. And we're talking about any object that is likely to cause a crash if the user fails to notice the hazard and execute an appropriate maneuver. Positive guidance should be designed to provide information along the entire hazard avoidance chain. So a hazard doesn't necessarily just mean a rock on the road or a log on the road or something like that. It could be a sharp curve, or it could just be the fact that there's an intersection here. And the hazard is that if you go into the intersection without following traffic control, you can get T-boned. So we need to give them enough information upstream of a hazard to detect it, to identify it, to decide what to do about it, and then to execute what has been decided. I'm just going to jump over now to human visual function and sign visibility. So we've talked about the driving tasks being complex. People need clear information to be successful in their driving task. So when we get them that information, we can't give it to them in a way that ignores how their visual function works. There are defined and quantified limitations to how people process information. And just like a structural designer would know some design parameters about steel, like its tensile, compressive strength, before designing with it, as traffic engineers, we need to know the design parameters of the human. So whenever I give a human factors course or introduction, we talk about these 6 areas of visual limitation. I want to touch briefly on some of them. And the more we know about those, the more we can design information systems that help drivers be successful, because we give information to drivers in a way that they can receive it. If you give information to someone in a way they can't receive it, it's not going to help them to be successful. Field of vision and visual acuity. what I really want to emphasize is that there's the field of vision is our peripheral vision, and it narrows from about 180 degrees at rest down to 40 degrees at highway speeds. But then there's a narrower cone within that, just in the center of that, that's only 3 degrees. And that's the field where you can resolve fine levels of detail, and you can do things like reading, legibility, judging intent, gap evaluation, etc. And that's only 3 degrees. And so, if the driver is here on the left, they have their slow peripheral vision, and then their highway speed peripheral vision is the darker gray and darker green, and the bright green is that narrow cone of visual acuity. A lot of what we do when we design traffic control or evaluate the safety of traffic control has to do with getting people to allocate a fixation of the visual acuity off to the side of the road. Because we can put it over the road sometimes, but oftentimes we can't. It has to be outside the cone of visual acuity. And then the big question is someone going to turn their attention to that? How long are they going to turn their attention to the side before bringing it back to the roadway? And will they comprehend stuff sufficiently in that short time? Some brief examples: this cyclist is within a cone of peripheral vision at rest, but not in the field of visual acuity, and probably not even the peripheral vision at the slow speed if this vehicle is going about 20 kilometers per hour. Here's another example, and I have 2 pictures where drivers are preparing to make a right turn on red. When they're making a right turn on red, of course, they're focused on scanning for gaps in traffic to the left in the traffic stream that they're going to join. And so any road users, pedestrians, or in this case, e-scooters approaching from the right are going to be outside the field of visual acuity. And so here's another person that should easily have been seen, you think should easily have been seen by the driver. And this, the video showed this pedestrian getting very angry, but the whole field of visual acuity was pointed way over to the left, and that driver was not successfully able to see that pedestrian. Here you have signals further out on the side and signals mounted over the roadway, and that's going to affect the amount of time that the driver has to be able to perceive and react to those traffic signals. Signs mounted over the road are in the field of visual acuity for longer and increase the chance of someone processing the information correctly. When signs are outside of the field of visual acuity, the brightness and the simplicity of the sign, we want to maybe turn our attention quickly to comprehend it very quickly. So you have a short symbol and it's a lower lateral offset here. And the goal here is to minimize the time of eye fixation away from the road so that they can get that field of visual acuity back in front of them, which is the natural position for that field to respond to alignment information and traffic information, which are kind of the 2 most important things that drivers need for executing their control tasks. The last quick thing I want to talk about is contrast sensitivity and eye adjustment. I want to highlight here, you see 2 vehicles. The first vehicle has high contrast with its surroundings, and it's easy to detect. There's a vehicle behind it with a dark vehicle in a dark location, and it's harder to detect, and it's because of the lower contrast. And contrast is the difference in luminance between an object and its surroundings. And when that difference is very small, it's hard to pick up the object. And when the difference is high, it's easy to pick up the object. And when contrast is high in our peripheral vision, it's a trigger to us that maybe something is important, and we're going to allocate one of our eye fixations, and we're going to either turn our head or turn our eyes and our sockets to go look at what this contrasting thing is that caught our attention. And when contrast is low, we may not even notice it's there in our periphery. And then if we don't notice it's there, we're certainly not going to choose to allocate an eye fixation over to it. Drivers can make up to 4 eye fixations per second at a peak performance, but they can't sustain that for very long. And kind of the sustained rate of eye fixations is 1 to 2 fixations per second. So here you have an example before we get too much more into signs. the amount of light coming back from a sign is going to influence its contrast. So if A is the amount of light coming back at you from the surroundings, which is pretty low at night, and B is the amount of light coming back from the sign, then B minus A, the difference is the contrast, and that's going to affect the likelihood of perception. So just to summarize this introductory section, drivers have many tasks to complete correctly, thousands. Task execution requires information. Positive guidance is about providing clear information for hazard avoidance. To provide clear information, we have to provide it in a way that accommodates humans' known visual limitations. And sign visibility is a controllable design parameter to accommodate human limitations. And sign visibility has a lot to do, well, there's many factors influencing it, but the ones I want to emphasize is that the contrast of signs and the placement. So if it's outside of that cone of visual acuity, the first successful thing that we need to accomplish is to get a driver to kind of catch their attention in that peripheral field to allocate an eye fixation over towards it. So the placement and the contrast are big factors. Of course, other things like the size, the placement in respect to how far in advance of the hazard and stuff like that. But those are different topics to talk about at a different time. I'm wrapping up here, and I'm going to pass it over to Amanda to talk about what we're doing with surrogate safety metrics to measure the safety performance of road facilities and traffic control treatments.
Thanks, Craig. I'm going to take over here and adjust your attention over to Menti. We have a follow-up question after Craig's presentation there. Interested to hear your feedback on some human factors practice areas that you think could be growth area in your agency. So Craig went over a couple of those today in his presentation, so curious to see your feedback on that. Great, well, thanks for that feedback. I'm just going to switch over. Is that slide coming through there okay?
It's good for me, Amanda.
Great. Okay. Well, thanks a lot for attending today. As Craig mentioned, I'm a road safety engineer at Microtraffic. My name is Amanda Pushka, and I'm really happy today to present to you guys on rapid before-after assessment using surrogate safety measures. And thanks for that feedback earlier, as I know a few of you are new to surrogate safety measures. So please feel free to ask any questions in the chat pod, and we'll get to that. A brief outline of my presentation today, I'm going to talk about why we use surrogate safety measures, some of the different types of surrogates and their sources, how surrogates are measured using video analytics, and particularly from the perspective of microtraffic. And then I want to go through some case study examples of rapid assessments for before and after evaluations. Okay, so why surrogates? Well, as transportation and road safety professionals, we often still rely on historical crash data to determine crash patterns and hotspot locations in our networks. And we understand that there are several problems that can limit this approach. And using this historical crash data can be both unreliable and reactive for a number of reasons. So first off, the data can be out of date. It may take a year or more to get that data back into the hands of practitioners who are analyzing it from either police sources or other sources. It can be underreported, especially for vulnerable road users. There can be inaccuracies in the data or limitations in the detail that's provided, so we may not know the exact configuration of a particular incident. There can be statistical issues due to small clusters of crash data. Oftentimes we're seeing fatalities occurring in a cluster of one, especially for vulnerable road users, which can really limit our findings. And then finally, historical crash data is spread across such a large network, and so we may find that fatalities are happening at locations where there have been no fatalities in the last 5 years. And so there can be this disrelationship between future and crash locations and current crash locations. And so at Microtraffic and others, we've started to shift our focus to surrogate safety measures. And so a surrogate is a non-crash measure of risk that proactively reveals risk factors with reliable sample sizes. And this isn't a new topic. There's actually a Transportation Research Board committee dedicated to surrogate safety measures. So I encourage you to look up that website and some of the research coming out of that group just to familiarize yourself with that. But by looking at these indicators or these near misses, we can be more proactive and precise about diagnosing risks to really enable this effective road safety improvement planning. And with microtraffic, oftentimes in our work, we're seeing a concerning frequency of serious near miss events happening for a particular movement at an intersection, regardless of any of the particular, or regardless of the previous recorded collisions there. And so it really indicates that a proactive action can be taken to address that risk. And so when I talk about surrogate safety measures, there's a number of different types we can look at, and they come from various sources. And so when we speak about near misses or conflict data, which is what we're going to focus on for the rest of this presentation, this looks at the very close interactions between road users. And this can come from just visually watching video and classifying that, or more commonly, it comes from artificially intelligence-powered video analytics. We can look at speed data, which is related to the likelihood of a severe injury occurring in the event of a collision. And this can come from radar, connected vehicles, and also from video analytics. We can look at exposure or volume data, and this is related to the probability of a collision occurring. So of course, the more interactions were happening between road users, the higher the likelihood of an event happening. And Craig talked about that humans' ability and human factors concept as our way to interpret and classify information. So if we have more information thrown at us, it's more likely to result in an error in the future. So this exposure data is one surrogate safety measure. We can rely on count programs, big data such as streetlight, and video analytics to provide it. And then one of the other surrogate safety measures is harsh braking events or evasive maneuvers. And so this can come from connected car data and aggregators, as well as from video analytics. And so at Microtraffic, our surrogate safety risk model is based on this kinetic energy principle, which acknowledges the fact that the human body is only able to withstand a particular amount of force in an impact. And this concept is really central to the safe systems approach that's been promoted in America by FHWA as well as internationally, and really helping us move towards this idea that we want to protect the human body from sustaining force. And so at Microtraffic, when we're defining the likelihood and severity of an interaction or of close near miss, we look at 5 key risk variables. And those are listed on the right-hand side of your screen. So we look at the speed of the interacting road users, the impact angle, the temporal separation, the user type and degree of vulnerability, and also the order of interaction. So for example, does a left-turning vehicle turn in front of an oncoming vehicle, or do they wait and turn behind them? And so the reliability of these surrogate safety measures is really important, especially for us at Microtraffic, we're based in road safety engineering principles. And so we have an ongoing relationship with Ryerson University, which is looking at the correlation between our near-miss data that we provide and the likelihood of a fatal or severe injury collision occurring in the future. And so we looked into this for one particular configuration type, and we found a 94% adjusted R-squared, which is the predictive power between our surrogate data and the likelihood of a severe injury crash occurring in the future. And so I encourage you to look up that paper if you're interested. It was published in Transportation Research Record this past January. So before we move further, I want to show some examples of near-miss data conflicts. So it might take a second here to load, but we'll play it a couple times. In this event here, I'll restart it, a bit of a glitch there. The cyclist violates the signal here and travels across, and luckily through an evasive maneuver by the cyclist, as well as the white vehicle slamming on their brakes, there's no collision that happens. But if we're seeing these types of close interactions happening between road users, it can signal us as transportation professionals that some sort of action has to be taken to prevent any collision from occurring in the future. Another example of a near miss here is on a rural highway. And so there's some snowy conditions, and you can see the vehicle makes a choice to turn in front of an oncoming vehicle with minimal separation there. And so these types of events could result in a severe injury or fatality. And the last example of a near miss is shown here. And so you can see the pedestrian is a little bit hard. Craig talked about that contrast sensitivity. It's a little bit dark on that crosswalk there. And so the vehicle turns without recognizing it. Once they do, they slow down and narrowly miss getting T-boned by the oncoming vehicle there. So one more time, we'll show you this event. So these are the types of events that we're trying to look at with surrogate safety measures, just as leading indicators for potential crashes happening in the future. And so how do we actually measure these surrogates? I'm going to talk from the perspective of artificially intelligence-powered video analytics, which is what we do at Microtraffic. And before all this, it really starts with collecting video footage. So we usually collect between 3 to 7 days of video footage using a temporary or permanent camera installed at an intersection. And so once we get that camera footage, we then have 6 main components to our technology. And it starts with computer vision and ends off with the output of diagnostic risk metrics for interacting road users. And so in step 1, that first image, the artificial intelligence models detect road users and classify them in every frame of the video. So you can see that the pedestrian has been picked up as separate from the vehicle. In step 2, we use a tracking system to link together road user detections in adjacent frames to create these green tracks that are shown in the image. In the third step, there's a spatial mapping is done, and it translates location of a user in the video camera lens into where they are in the real world location in the intersection. And this requires undistorting the camera lens and creating a relationship between pixel coordinates and the real world location in the intersection. And this is really important because it allows us to derive speed and relative proximity of road users. In step 4, trajectories are developed, and then the intersecting trajectories are then filtered down based on the criteria that we use to define a near miss. And I mentioned those 5 factors previously. In step 5, we take these near-miss interactions and our risk models, and then we develop scatter plots for each encounter of a particular movement. And so in image 5 there, each one of those dots represents one conflict event happening for a particular configuration. So for example, a left-turning vehicle versus an oncoming car. And so each of those dots represents a conflict or a near-miss event. And on the x-axis there is the temporal separation. So as we move left across that x-axis and become closer in time, they become a more severe interaction. And as well as if we go up that y-axis, which is the speed of the impacting vehicle, it becomes more critical. So that red box in the upper left corner is the most critical events that we see for a particular movement. And then we take these scatter plots that are shown in image 5, and we compute this for a variety of different possible conflict configurations at an intersection. So there are 16 different ones for vulnerable road users shown in slide 6 there. We also look at vehicle-vehicle interactions as well. So that was a really quick overview to surrogate safety and an example of what near misses look like and how we actually compute that using artificial intelligence. But I want to touch now a bit more on rapid before and after assessments and why this is valuable. And so a lot of times we rely on crash data to evaluate the impacts of safety improvements, but we generally have to wait for a minimum of 3 years and even preferably at least 5 years when there's sufficient crash data to do a full assessment of the change in safety trends. However, with conflict data, we can get a large enough sample size in a relatively short period of time that we can start to assess our safety performance within 1 month. And so these rapid before and after assessments really start to enable agencies to trial new treatments, low-cost treatments, understand how other established treatments are working within your jurisdiction, and really provide justification for larger improvement investments as well. So the first example I want to share with you today is a rural highway example, and this is a location in British Columbia, Canada, so a very mountainous region in the country. And so what we looked at here and what I'm presenting on right now is the configuration of a minor road stop control across a major highway. So this truck here is on a major highway that's operating at 100 kilometers per hour or 60 miles an hour. And vehicles are on a stop sign here turning left onto the highway. And so you can see this van and trailer is pulling in front of the truck to turn left onto the major highway. And so this is the conflict configuration we're looking at where the driver door could be impacted by an approaching vehicle. And within a couple of days of measurements, we detected 75 high-risk conflicts and 12 critical risk conflicts in that period. And the interesting part is that of all the vehicles turning left, nearly 7% of them were involved in a high-risk conflict and 1% in a critical risk conflict. So a pretty high proportion of vehicles turning left. And at Microtraffic, because we looked at so many different configurations and locations, we can start to look at similar locations with similar features and look at the average conflict rate that we see to start to understand how do sites compare to one another. And so at this location it was actually 18 times higher of a conflict rate we found here compared to our average locations. And so this was flagged to the DOT we were working for and created they wanted to respond to this. And so I mentioned that it's in a mountainous region, so the implementation of a roundabout or a grade separated crossing may not be feasible. And so they had to do some additional studies, but in order to address the risk they were seeing, they decided to put in a low cost treatment. And so what they put in was an ITS solution, or an intersection conflict warning system, which alerts drivers of vehicles waiting on the minor road. And so this low cost solution, which was only a couple $100,000, they were able to put in, and they did a rapid after measurement to see, okay, how much risk reduction occurred and how much risk is remaining. And so with this after measurement, we saw a complete elimination of critical risk events and a big reduction in high risk events. And so we went from a conflict rate of 7% down to only 2%. And although there is still some residual risk remaining, there's been a big steps made to improve safety at this location. And so this low cost solution, it was able to do a quick assessment to see what kind of risk was remaining, and they can use this data in prioritizing additional improvements in that location. I want to share briefly an urban example. We hear a lot about leading pedestrian intervals right now as a way to improve the visibility of VRUs on a crosswalk by allowing them to establish themselves into the intersection by advancing the walk signal prior to the green signal for vehicles. And so this has been a treatment that's discussed, especially for right hook conflicts. So you can see this vehicle turning right. The pedestrians are already established into the intersection, and improves the sight lines for the drivers. And so at this urban location, not a ton of conflict data, but we saw 14 medium risk conflicts that were detected in around a 60-hour analysis period. And the conflict rate of this was about 0.3%. So not an excessively high number, but still notable in terms of the number of people that were engaged in a conflict event with the vehicle. And so the city decided to implement a leading pedestrian interval, or an LPI, and added some visibility enhancements with the zebra or continental crosswalk markings. And you can see this is the after implementation. So this walk signal is on while the adjacent signal is red. Oh, sorry about that. We'll just jump back. And we went back and measured the risk after, and in a similar duration period, we only detected one conflict. So the conflict rate dropped down to 0.04%. So doing this low-cost signalization change and visibility enhancements, other low-cost solutions, there was able to be a reduction in risk for vulnerable road users. And the last example I want to share today is with roundabout performance. So we understand, we've heard the performance of roundabouts at reducing the collision severity by lowering the impact angles and the speeds at which vehicles can travel through there. So we did a quick assessment of one of these locations in Canada. And for this movement here, where a vehicle is turning left across a highway, these are two high volume highways, you can see a high number of high and critical risk conflict events occurring at that location. And when the roundabout was implemented, all the different configurations showed full reductions in critical high risk interactions and all into low interactions. So we're dropping down that speed and improving safety. And so doing this quantitative assessment of performance, we can really start to drive larger investments into road safety. So to summarize today, I outlined a bit about what surrogate safety metrics are and how they can be used to complete rapid assessments of intersection safety performance. So without being reactive and waiting for collisions to occur to assess if we've addressed that risk, we can be proactive and go out right away and determine what kind of risk was reduced and how much risk remains. And so these rapid assessments are really helpful for improving our understanding of the impact of low-cost treatments within your agency, as well as the remaining risk, and also for providing quantitative justification for road safety improvement investments, such as a roundabout. So thank you so much for listening to this portion. We're happy to answer any questions in the question pod, and we'll have a Q&A period at the end as well. And so I just want to jump back over to Mentimeter for a follow-up question here. So if you can navigate over to that tab. And so I'm just curious if your agency does any before and after assessments. I know sometimes it can be really challenging, but I was wondering if you do any sort of evaluations and what that looks like, whether you have done it in the past or rely on crash data. Curious to see your response here. Nice to see that some rapid assessments or rapid evaluations have been done. But as expected, a lot of reliance on this historic crash data. So that concludes my section. Craig, do you want to pass it over there to Todd?
Yeah, Todd, feel free to start setting up for the screen sharing. I want to welcome Todd Ballin, Dr. Todd Ballin, Senior Product Development Specialist at 3M. He's an expert in all things about visual optics, sign reflectivity, and how they design products that are geared towards helping people get the information they need from signs. They have some high-tech signs that we're going to be doing a study to use surrogates to measure the effectiveness of these signs in reducing conflicts. But he's going to talk a little bit about these signs, how they relate to standards, why is it important. We're very pleased to have him with us. Dr. Ballin, please go ahead.
Sure, just a second, Craig. I'm trying to get myself back to my meeting controls to turn on my video.
Once you start the screen share, those controls disappear unless you kind of navigate to the top of your screen share, and then they'll kind of drop down from the top.
Okay.
And while they're hovering down there, you kind of got to hit that video button. You can also stop your screen share and then restart it as well.
Okay, maybe that's the simplest way to do this.
You're there. I will go away.
All right, perfect. Okay, thanks very much for the introduction, and thanks to Amanda for the poll. I think it's very good to have a chance to see where folks are located. So good morning, good afternoon, and good evening, since we have some international colleagues as well. And so as described, my name's Todd Ballin, and I'm from the 3M Transportation Safety Division. And it was also very instructive, I think, one of the poll questions that Amanda asked to get a sense of how familiar folks are with type 11 sheeting, and to see that we have a range of familiarity. Some people that are clearly very familiar with type 11 sheeting, and some folks that are brand new to this. So I hope to be able to satisfy the needs and interests of both ends of that spectrum, and we'll go ahead and get started. So one of the things, as Craig described, the ASTM D4956 sign sheeting specification describes various types of sheeting, and type 11, as Craig mentioned, is the highest performing, has the highest retroreflectivity values in that. And it's important, and one of the things that I'm going to spend some time that we have together here today doing is to dig a little bit deeper. When you look at that specification table, there's a series of RSAB, retroreflectivity coefficient values, and type 11 is more than just the sum of those values. Really what that type 11 requirement provides, as compared to some of the historical types of sheeting, is performance at a wide range of viewing conditions. And we'll get into a little bit more depth of what this really means. But it establishes performance to say that across a wide range of viewing conditions, this sign sheeting will be providing very good performance. And so one of the things that we need to then do is consider how do those requirements, how does that performance of the sign sheeting connect to the driver performance, the kinds of things that Craig described in his opening section. And so in order to do that, we'll go back and look at some of the historical, the older technology, the lower type numbers, and see how those behave. And so those, particularly with the movement from glass bead related sheeting to prismatic sheeting, type 4 and for example, type 8. Many of those truncated cube sheetings have approximately 30% efficiency. That means of the light that strikes the sign with that type of sheeting, 30% of it reflects back generally in a direction that could be useful to the driver. And so some of those earlier types, type 4 and type 8 that I mentioned, return that light in a cone of retroreflectivity shown here in green. And that was that cone, that divergence profile, the spreading of the light, is designed so as to send light back to passenger vehicles. And so that's fine for someone in a smaller vehicle. But as soon as you shift to a larger vehicle, those types of products tend not to distribute light very effectively to a large truck. The driver of a large truck is going to receive very little light. And so that's a problem. And over the historical development of sheeting as described in the ASTM standard, there was a type that was introduced, type 9, which took that same approximately 30% efficiency and chose to expand the cone of retroreflectivity, to broaden it, so that some light would be directed to drivers of large vehicles. And so that helps, but then the result of that is that a significantly smaller fraction of light is available to drivers of smaller vehicles. And so, that represents a compromise that the truncated cube sheeting is faced with. There's this choice between, with the limited amount of light available, where is it going to be distributed? Which vehicles are going to be served? And how is that all going to work? And so if we look a little closer at the geometry of truncated cube corners, we can start to understand where some of those limitations come from. And so this drawing shows a schematic of a small array of nested truncated cube corners. And what we see is when light enters and reflects inside the cube corner, light that hits the tips of the cube corner, those regions marked with the red triangles, only reflect twice within the cube corner and are not retroreflected. In order for the light to be properly retroreflected, it has to bounce 3 times inside the cube corner. And so that means that only about 2/3 of the area of the cube corner is effective, is optically active. And so that's shown by superimposing these blue regions. So within each one of those cube corners, when light strikes within that blue hexagonal region, it retroreflects. If it strikes outside of there in the tips, it does not. And so what we then could imagine doing is thinking carefully and saying, well, why, with this truncated cube corner where we have these dead regions, these regions that are non-functional, what would happen if we didn't actually make those? And so the approach that 3M used to make the full cube type 11 sheeting is to focus on the rectangular region that's highlighted in red, that you see completely lies within that blue region that retroreflects. And then by only making that portion of the cube corner, and we'll step forward through a little animation that shows as we reproduce those portions of the center part of each cube corner and bring those together in an array, that results in what we call a full cube corner, in that the full optical aperture of the cube corner is functional. So it has theoretical 100% optical efficiency. And then once this is translated into actual sheeting, there are reflection losses getting the light in and out of the sheeting, and some other characteristics of the way the sheeting is constructed results in nearly 60% efficiency in the 3M DG cubed full cube type 11 sheeting product. And so if we go back to what we looked at before with how the sheeting interacts with the driver, now if we take this nearly 60% in the type 11 sheeting, and we can have a broad cone of retroreflection, like we described before with the type 9 sheeting, but we can distribute a substantially greater portion to both drivers of smaller vehicles as well as drivers of larger vehicles. So this way we're able to remove some of that compromise that's present with truncated cube sheeting by being able to serve drivers of multiple vehicle sizes and then multiple geometries, going back to the variety of different sign locations that Craig mentioned in some of his comments. So this sort of description and this understanding of type 11 sheeting may be some things that some of you may be very familiar with through your past exposure to the ASTM sheeting types. But I wanted to also bring into our discussion today some current research that's been done that helps us to understand some of the real value of the type 11 sheeting. And the first one is looking at headlight distributions. And in particular, over the passage of time, the distribution profiles of vehicle headlamps continue to change. And the University of Michigan Transportation Research Institute, UMTRI, that some folks may have heard of, has, over the course of the past decades, occasionally published studies of headlamp output, where they will sample and generate market-weighted averages of the headlamps in vehicles that are being sold in a given year. And so just recently in 2019, they published the latest version of this study. And this allows us to go back and compare to the prior study that they did, which was 8 years before that in 2011. And so then this is an output on the top showing as a function of angle, both vertical angle and horizontal angle, the output from the headlamps. And then you see superimposed on top of those some theoretical sign locations, a left shoulder, an overhead, and a right shoulder sign location. And as you can imagine, as the vehicle is traveling towards the sign would actually be moving in the distribution space, so that when the vehicle is very far from the sign would be located in the center, and as the vehicle drives toward the sign, it would move outward in angle space. So what we did at 3M is we took these distribution profiles for these headlamps and calculated the illuminance, the amount of light that is striking a sign at some of these characteristic locations, using the new 2019 headlamp data as compared to the 2011 data. And we found some interesting things. In particular, you could see here that this is the horizontal axis is the distance of the vehicle from the sign location, and it changes over the course of that. But if you look at sort of the grand average, in each one of these situations, left shoulder overhead and right shoulder sign, the 2019 headlamps are delivering significantly less light to that sign location as compared to the 2011 version. And that's important because as you think about how bright the sign is going to appear, the efficiency, the retroreflective coefficient of the sheeting is an important component of that, but the amount of light that strikes from the vehicle headlamps on that sign is going to directly impact the perceived luminance of that sign. So as we see these 10 to 15 to 20% reductions in illuminance on the sign, that means that sign with the same sheeting that it currently has on it now appears 10 to 20% less bright than it did before. So in order to preserve the brightness of the sign with these more modern headlamps that are delivering less light to the sign, the effectiveness of high performance sheeting such as type 11 sheeting becomes increasingly important. And so that's one component. And then the other is starting to look at some of the driver needs. And Craig did a great job of describing the driving task and many of the things that the drivers need to be concerned about. But there was a study that's been done that helps us to understand how signs are viewed based on the complexity of the surrounding area. And in particular, when we look at urban versus rural driving, as we move from rural areas into urban areas, the background complexity, the amount of distraction, the amount of other objects that are within the viewing field, draw the driver's attention away from signs. And so there is an increased need for luminance of signs, and in particular for the presence of glare sources and other things. The amount of luminance that the sign needs to be generating in order for drivers to be able to accurately read the sign and get the information that the sign is conveying needs to approximately double. And then further, there's an NCHRP report 828 that looked at the presence of signs in various settings and classified them into these different complexity levels, these different visual complexity levels. And some example illustrations from that NCHRP report are shown below. Starting from on the left side, level 1, where this is rural, there are very few other objects in the field of view. There's limited complexity, and then gradually introducing some complexity over the course of as we move to higher and higher levels, so that we're moving into increased commercial activity. There may be other lights, there might be other illuminated signs, there may be oncoming traffic, and that by the time you get to level 5, there's very substantial complexity here, lots and lots of background noise that will make it challenging for drivers to see signs. And then on the basis of defining these different levels of visual complexity of the background, the researchers carried it a step further and said, well, what sort of sign sheeting types are helpful in these situations? And so as a result of doing this, they evaluated the recognition index as compared to the luminance of the sign, which is tied to the sheeting type, as well as the visual complexity, the connection to those visual complexity levels. But the main takeaway in this is that as in some of the lower complexity levels, so this complexity level 1 and 2, mostly rural areas, it really doesn't matter as much. A wide variety of ASTM sheeting types can be effective in those situations. But as you move to higher and higher complexity situations, getting into some of the urban areas, it becomes increasingly important to use high performance sheeting in order to have the sign have sufficient luminance for the driver to be able to pick out the details against the background distractions. And in some situations, it actually gets that there can be so much background that even type 11 sheeting, the most efficient sheeting, may not be bright enough, and external lighting is sometimes recommended in some situations. But that's an interesting way, I think, to help connect the performance of the sheeting to the way the driver's interacting with it and getting information from the sign. So to summarize the section that we just covered here, I wanted to convey that the ASTM D4956 Type 11 sheeting requirements are more than just a table of numbers, as I suggested, and it describes performance across a range of situations, vehicle types, those sorts of things, and that there are some very current studies that help to highlight the continuing importance of Type 11 as vehicle headlamps change, and as we consider the background complexity of things such as urban environments. All right, so with that, I will end my portion.
Todd, thank you very much for sharing your knowledge on this, and I think it's fair to say that people really learn a lot through presentations like that, like what's the difference between full cube and truncated cube, and the manufacturing process. And I know I did not know until about a year ago about this trend with headlights, which I kind of find very concerning, right? the sign can only give back a part of what it's given.
Yes.
And now we're giving less to the sign. So
Yes.
the performance of that sign and its ability to give back the little that it's given now becomes even more important.
It does. Yes.
Yeah. So that, and I think a lot of engineers didn't know. I mean, I've been working in road safety a long time, and I only learned a year ago about this trend with headlights. That's concerning, and I think more engineers need to know about it. So I'm glad you brought it up. Matt, are we doing another Menti right now?
Yeah, we just have a couple follow-up questions that focus a bit on retroreflectivity. The first one is that Todd didn't really get into this in his presentation, but the MUTCD talks about just different acceptable sign, retroreflectivity, maintenance methods. So we talked about the installation of signs. We were just curious if there's any sort of steps that your agency would follow to check for when those signs need to be replaced. So what kind of maintenance methods are there? And if you guys are aware or you're not sure, we'd be interested to see your feedback there. And the last question here that we have for Menti is, a number of you have said that you've used Type 11 sign sheeting in the past. Some of you said you haven't used it before, but this is one where you can actually type in any answer you'd like. So we're just curious if there's how you've applied these. So Todd talked about the performance of them in rural versus urban locations, but have you used Type 11 for regulatory signs or warning, guidance, or otherwise? Curious if you have any feedback to provide there.
Yeah, you talked about high complexity locations, low complexity locations.
Maybe we'll keep that running in the background, Craig, if you guys want to take over and do your last presentation, and we can always revisit that at the end.
Yeah. So these things will keep popping up, and we'll pull it back up once, because typing out the answers takes a little longer here than just clicking on an option.
Yeah.
So yeah, please continue. Don't leave the Menti while I get my screen share started. Okay, so now John and I are going to be talking a little bit about pooled fund project, which is a way that you can put into action and practice some of the things that we've talked about today to generate new information about these signs. The reason we're doing this is there's a lot that is clear and abundantly known about the light reflective properties of these signs. And there have been studies on legibility, there have been studies on, the perception, the recognition, the truck angles, the car angles, and all that kind of stuff. But then you get into what's the real world impact on safety? And there is a knowledge base on that. There's some very interesting publications on the real world safety impact in terms of crash reductions and incident reductions. But that knowledge base does need to be expanded. And it needs to be expanded to help people make more informed decisions about sign sheeting, because it's no secret that the higher performance grade of ASTM standard you're picking, the higher the cost of that sign sheeting material, at least upfront costs. Some of it lasts longer too, so lifetime cost is lower. But what's the safety benefit there to justify that? And that's what we want to do with this we'll call it industry-initiated pooled fund project. So we're aiming to better guide standards, specifications, and systemic safety programming. But another objective is this project is that at the actual study locations, we want to provide precise diagnosis of all the road safety issues, sign-related issues and non-sign-related issues, so that you can understand, okay, well, I have a location of concern. It goes into this pooled fund project. It gets totally diagnosed with the surrogate video analytics, and you understand sign-related risks and all kinds of other risks that you could respond to and make proactive road safety improvements at that intersection. So it gives you a chance to try the microtraffic technology. The way the project is structured, it's a collaboration between DOTs, Departments of Transportation, Microtraffic, and 3M. We will be conducting before-after evaluation of Type 11 sign retrofits at 50 locations. We will be using video analytics to measure changes in surrogate safety indicators such as near misses, speed, and stop sign compliance. It's kind of partly DOT led, in that we have a number of site types that we're interested in, and we plan to do up to 2 site types, so then there will be 25 sites per type, or 1 site type with all 50 sites of that type. And we're just kicking this off. So as the DOTs sign up and indicate their interest, we will tune the site types according to that interest. And there's a number of site types that we could potentially select from this list. We'll take up to 2, and potential future extensions of this study, depending on interest, could address other site types. This is a pooled fund project model where there's a $580,000 main budget for the project, plus DOT in-kind contributions. The main budget of 580 is 50 sites times 10,000 per site. That's a pooled fund participant fee. So you're getting diagnostics at your intersection before after video analytics, and according to the number of intersections you're going to have in the study, that would, times 1 intersection, times 2 intersections, times 3 intersections, that's going to determine the pooled fund participant fee. That covers the before after video analytics, the risk reporting specific to your DOT for sign related and non-sign related risks, and the identification of countermeasures. So it's kind of like paying for a road safety audit at that location and gaining the benefit of that, except that it's powered by AI technology. And then the 3M contribution covers study design, project management, the global analysis, reporting, and peer-reviewed results publication by Microtraffic acting as independent researchers. The DOT in-kind contributions required by a participating agency include collecting the video, implementing the sign replacements. So you got to grab some Type 11 sign sheeting, DGQ specifically, diamond grade, and putting some time into site selection and the project steering committee meetings. Video collection happens a few different ways. If you're a rural DOT, we have a video equipment rental partner. These people rent work zone equipment to almost every DOT and traffic control company in the United States already. And they have a camera trailer that's perfectly suited to this kind of study. And we would have you contact them and grab a trailer for 1 week, 2 weeks, 3 weeks, depending on how many sites that you're going to be analyzing. So there's a cost to that that's separate, but a lot of people already have access to these trailers. If you have your own equipment, you can use that instead of renting from Street Smart if it meets the study spec. And for urban DOTs, a variety of collection methods are possible. You can use a video collection contractor. Often in cities, there are people that go around with these telescoping poles to do traffic studies. Some urban DOTs have their own MyVision Scout units. Scouts can be used in urban locations where there's sufficient ambient lighting. Rural DOTs cannot use Scouts for this study because of the lower street lighting levels, and Scouts don't have something called wide dynamic range on the camera. If you have existing CCTV or pan-tilt zoom cameras, they can be used together, and we work with the agency to make the video collection plans. We're looking for agencies to select sites that are kind of safety concerns, collision prone, so you really get the benefit of that diagnostic safety audit of the site. You may trigger, a very substantial safety improvement that goes beyond the signs. You need to do the signs first so that we can measure the before after and put the site into the study. But you may also see risks that provide justification or clarity on some other, very substantial countermeasures, and we can assist you in working through that diagnostic data. So we don't want you to pick locations that you don't feel are a safety concern. So it should be kind of a safety concern location that has some characteristics. If we go clockwise around the circle, that might make it subject to elevated perception failure risk. So is there a lot of background information going on that would lead a driver to have a perception failure incident? Or is in a rural area, is there big speed changes that need to be perceived, or horizontal or vertical curvature, or sight triangle issues that might make an intersection a bit harder to perceive? So that would be an attribute of a good site. And then, of course, the existing signs have to be something lower than type 11, right? So we're going to measure the change in safety surrogates from going from an existing sign, like maybe it's type 5 or type 9 or something less than type 11, and moving it up to type 11. So I'm going to pass it to John Lauer. John is Vice President of Safety Partnerships at Microtraffic, spent a long time leading transportation at the city of Anaheim, and he wants to talk about kind of looking back to that perspective as a DOT kind of manager. What are some of the benefits of participating in a pooled study like this? And I give it to you, John.
All right, thank you, Craig. Yeah, as your agencies give consideration to participation in this study, we want to highlight 3 benefits. But before we dive into those, I want to share with you some wisdom that was passed on to me over 30 years ago by a mentor who was coaching me as I stepped into a role leading transportation systems management and operations in a major city, the city of Anaheim. And what that wisdom was that you as a TSMO leader, transportation systems management and operations leader in a public agency, need to be asking yourself 2 questions every day that you leave the office. The first question is, are things getting better or worse? And the second question is, how do I know? So with that perspective, let's look at this first participation benefit. You're going to have diagnostics at your selected sites, and that's going to set you up with a solid baseline of risks, those 5 risk variables that Amanda had mentioned. And it's going to allow us to develop responsive intersection countermeasures, coming back to you with the effectiveness in months rather than years. So that's that rapid measurement. You're also going to be having a trial of this video-based surrogate analysis, which is going to help you answer that second question, how do you know whether things are getting better or worse? So the second benefit, Greg, if you can move our slide on, is the measurement of residual risk at your selected sites. So what we're going to find out if the sign retrofit adequately addressed the problem. Is there a need to proceed to more expensive countermeasures? Microtraffic's been around for 3-4 years now. We've helped over 70 agencies, partnering with them to identify the most effective countermeasures. And in that process, saving over $140 million in projects, which would have been which would have resulted in not the most effective countermeasures being implemented. So with our baseline diagnostics, you're going to have the most cost-effective countermeasures put into place. So in other cases, when you're, as the professional, trying to talk to your budget analyst, your directors to justify a more expensive project, you'll have that data on supporting that need. And then finally, the third participation will be obtaining a global study, these 50 sites, to know where and how this type 11 sheeting worked best. So you're going to know how much better your sign program is. And with that, you'll have implications for data-driven systemic programs. That is something that is expected in the US to come with the infrastructure bill, focus on systemic programs. We'll have implications to be considered for standards and specifications, and put your DOT in a leading role to pick up where the AMU-TCD currently leaves off, and maybe even influence that ongoing process. So with that, I'll turn it back to you, Craig.
Thanks very much, John. I just want to, just before we kind of rapid fire deal with some of the questions in the chat, outline 2 ways that you can participate in this effort. You could join the pooled fund project. Okay, you could say our DOT, we're in with 1 site, 2 sites, 5 sites, 10 sites. It's calibrated on that per site basis with what you can invest. I think a lot of DOTs on this call have already done a study with microtraffic. Okay? So if you've already done a study that's used as the before study, okay, we cut your per site contribution in half, right? Because we just have to do you just have to change the signs, and then we do the after analytics. So there's a potential to save money off of that participation fee. A lot of agencies have already done studies, and if that site happens to line up with a good site for this study, and we use the before analytics from that. But you say, yeah, we can put 5 sites in. We're going to invest in generating this knowledge base. If you can't join the pooled fund study, whether you can, whether you can't, or you're still thinking about it, I want you to participate in a jurisdictional survey on the use of type 11 sign sheeting. And what we're going to do is we're going to publish this survey alongside the global study results in a way that's going to help you understand pure practice. What are other DOTs doing with this stuff? Have they tried it for regulatory signs only, or regulatory and curve warning, or freeways only, but not state highways? We're going to talk about that stuff, or stop signs only. You'll see what your peers are doing, and kind of learn from that. Not that you have to do what they do, but we'd love you to participate in this jurisdictional survey. We're going to email you after this webinar. Through your registration, you shared your contact details with us. So a member of our research team is going to email you with a link to book 30 minutes for the jurisdictional survey. We do that kind of over a video chat, over Zoom or Teams or something like that. There's about 10 questions, 30 minutes, and it's very conversational based. We'd be honored and grateful for you to do that. And you do that even as you're thinking, in that chat, we'll talk a little bit about whether your DOT can keep thinking about participating in the pooled fund project, any questions you might have about that. This concludes kind of the formal part of our webinar, and we have a little less time than we planned, but we do have time for some questions, and I think we should take that. I'm going to open up the Q&A panel, and maybe uh, you know, I'm going to go to the first question, maybe ask Amanda to respond very briefly to it. There was about PET thresholds to segregate critical and non-critical conflicts, and I know it goes beyond PET. And there was another question, why just PET? Do you use other temporal separation metrics as well? That was in the chat, but not the Q&A. Amanda, could you maybe tackle both those together?
Sure, yeah. So the PET thresholds we use at Microtraffic are different for vehicles and VRUs based on research that's come out of Australia about the body's ability to withstand force and your probability of severe injury in the event of a collision. So we reference those values with, it's different depending on person versus vehicle. So 15, 35, 50 kilometers per hour. But happy to please send an email so I can talk a little bit more. I know we're tight on time here. In terms of other metrics, I showed examples with PET, but when we look at vulnerable road users, we use a different metric called T2, which is like a time to collision type metric. So please send me an email and I'd be happy to discuss that in more detail, but I know we're tight on time here.
Thanks, Amanda. Yeah, there's lots to talk about that. And I'm going to maybe pass two questions at a time to Todd. They're about headlights. Tammy is asking about high beams. She believes that the information was specific to low beams. And Fadi, interesting question. As the headlamp distribution, if that trend continues, will there be a need for more advanced reflective sheeting than type 11? So maybe you can tackle both of those pretty briefly, Todd.
Sure. Thanks for the question, Craig. So with respect to the high beams versus the low beams, so the particular UMTRI report, the 2019 report, did not include high beams. UMTRI has occasionally in the past studied high beams, but this time, they do more often, it was focused on low beams. I guess I will highlight that there was one edition where they looked at both tungsten halogen low beams as well as LEDs, and this was the first time they looked at LED low beams. But so no high beams, but some new material there. The second one about changes in the headlamp distribution, it's hard to predict exactly how much the distribution could continue to change. I think at the present time, Type 11 sheeting does a good job of compensating for these reductions. But at some point, there could be some challenges. I think we would have to look and see how much the headlamp distribution changes to see if there's a need for that. They can't, the headlamp designers can't completely get rid of light that goes above the horizon that would be directed onto headlamps, so that there will always be some. It's a good thing to watch. It's an important question.
Hey, thanks a lot, Todd. Maybe Gina, if you're welcome, if you're interested to, I wouldn't mind passing the last question to you. They're asking about autonomous vehicles, connected roads, camera readability of signs. And I feel like this is an emerging area of market development for 3M. And if you have some brief comments on it, I think it's important. I know people like Tesla come out and say, hey, wider pavement markings, please, on the edge of the road. And that'll help us stay in our lane better. What do you know about machine readability of signs and what you see coming down the future of that, Gina, that you might like to share? I'm putting you on the spot because you weren't geared to present here.
Yeah, that's okay. Thanks, Craig. I think I'm gonna throw this back to Todd. He's in our lab, and I think he probably has more visibility to what 3M is doing around this.
Yeah.
And what's happening with respect to signs.
Okay, Todd, real quick, what's coming with machine readability, camera readability?
So certainly camera readability of signs is important. One of the big challenges that we hear from some of the manufacturers is that for the most part, the signs are plenty bright enough. They are sufficiently reflective currently for cameras. Sometimes it's a contrast issue that you highlighted where the camera can actually have issues with that. So I think it will be an interesting space because as we continue to develop in the automated vehicle space, we still need to service the needs of the human driver. And so there will be this counterbalance between the specifics of what the cameras need, but continuing to as we have historically, provide sufficient light to the human driver. So something to watch for, but it will become increasingly important.
For sure, yeah. And then the contrast becomes important, not just the sign and its surroundings, but the actual the material on the sign, the legend, and the background.
Yes.
Right? So you need the sufficient contrast there. And the METCD might need to be updated on that. And certainly some cameras are better at handling low levels of luminance contrast that other, if they have that wide dynamic range or not. And we deal with that all the time. We'd much rather get footage coming from a wide dynamic range camera, but we don't always get it. Look, we're right at 12 o'clock Central. Thank you, everyone, for your time. Todd, thank you for sharing your expertise. Amanda, John, thank you, DOTs, and everybody for coming to learn about this topic. Whether or not you participate in the study, I hope the content on reflectivity, surrogates, and human factors has been valuable for professional development. And we're going to be in touch about the jurisdictional survey and potentially joining the study. The recruitment period will now go on for the next, probably a few months as DOTs make their decision. And we'd love to have you join us in one of those two ways. Thank you, and I wish you a very good rest of your day. Goodbye.